Another way to find point estimators in a situation when each single observation depends on the unknown parameters in its own way is ordinary least square method or OLS method. So let's imagine such a situation that we have 4 observations, y1, y2, y3, y4, and we have 2 unknown parameters, alpha and beta, and each y depends on these parameters in its own way. So y1 is alpha plus beta plus epsilon 1, y2 is alpha minus beta plus epsilon 2, y3 is minus alpha plus beta plus epsilon 3, and y4 is minus alpha minus beta plus epsilon 4. So here alpha and beta are unknown parameters to be estimated, and epsilons are errors. So alpha and beta are parameters to be estimated, and epsilons are errors, and it is given that they are normally distributed and independent. So all epsilons follow normal distribution with the same with zero mean and given variance, and epsilons are independent. And so we are to find estimators, point estimators of alpha and beta using this ordinary least squares method. So what this can mean in practice? So we measure several values that each of them depend. So each of them depends on the parameters, but this dependence is different for each observations, for each value we are measuring. So while measuring, there are measurement errors. Measurement errors are usually described as the random variables with a normal distribution that have a zero mean. So expected value equal to 0. So this OLS method is just minimizing the errors. So we assume that these errors between what we would get if there were no errors and what we actually got. So error is a difference between, so alpha, for example, alpha plus beta is what we would get if there were no error, and y1 is what we got in practice. And the difference between what we would get and what we got is actually the error. And so we assume that these errors are not so very big, so that our measurement is maybe not absolutely accurate, but still pretty accurate to assume that errors are small. And that is why we say, let's try to minimize sum of square of errors. So we use RSS term for this function. RSS is for residual sum of squares. So, and RSS is equal to the sum of squared errors. So epsilon 1 squared plus epsilon 2 squared plus epsilon 3 squared plus epsilon 4 squared. And then we express epsilons via y's and alpha and beta. So epsilon 1 is y1 minus alpha minus beta. Epsilon 2 is y2 minus alpha plus beta, and so on. So I say that this is y1 minus alpha minus beta squared plus y2 minus alpha plus beta squared plus y3 plus alpha minus beta squared plus y4 minus plus alpha plus beta squared. So this is the sum of squares. And now the idea of the ordinary least squares method is to estimate, to find such values for alpha and beta. The estimators are such values that minimize this sum of squared errors. So I am to minimize this function as a function of two arguments of alpha and beta. So to do so, I am to differentiate this function over alpha and over beta respectively. So partial derivative of the RSS function over alpha is two times y1 minus alpha minus beta times derivative of this expression over alpha, that is minus 1, plus 2 times y2 minus alpha plus beta times the derivative of this expression over alpha, that is minus 1 also, plus 2 times y3 plus alpha minus beta times the derivative over alpha, that is plus 1, plus 2 times y4 plus alpha plus beta times derivative over alpha, that is plus 1. So, and we equate this to 0, and we find the derivative of the RSS over beta and equate it to 0 also, and get the system of two equations. So this expression will be very similar. Difference is only in signs. So 2 times y1 minus alpha minus beta times minus 1 plus 2 times y2 minus alpha plus beta times plus 1, because beta is with plus here, plus 2 times y3 plus alpha minus beta times minus 1 plus 2 times y4 plus alpha plus beta. And we equate this to 0 also, and this is the system of two equations. So we can simplify this system if we add these two equations one to the other, and add and subtract. So if we add the first equation to the second one, what will we get? And by the way, we can also divide all these by 2. So these 2 disappear. And then if we add the first equation to the second one, we see that this element and is equal to this one. So when we add the first to the other, to the second, we get 2 times y1 minus alpha minus beta minus 2. Then this one and this one are of the same value but of different sign, so they annihilate each other when we add the first equation to the second one. So this and this are also of the same value but of the different sign, so they also annihilate each other. And this and this are of the same value and of the same sign, so we add them and we get 2 times y4 plus alpha plus beta. So this is what we get after adding these two equations, and we can also then here not minus but plus, and so these two also disappears. And then if we substitute subtract the second from the first one, so these are of the same value and of the same sign, and they annihilate each other after subtraction. These are of the same value but of the different sign, so we have minus 1 and then also minus 1 minus 2 y2 minus alpha plus beta. So these are also of the same value and of different sign. So this minus this is plus 2 times y3 plus alpha minus beta, and these two disappear. So after this kind of simplification, we get this system of equations, system of linear equations. Or we can also simplify it, and after further simplification we'll get what? So here y1 minus y1 plus y4 minus y1 plus y4 minus alpha plus alpha, so alpha disappears, it should not disappear. So here I have minus, yes, minus alpha plus alpha minus beta minus beta is plus beta. So alpha plus 2 alpha and beta plus 2 beta. And here, so minus y2 plus y3 minus y2 plus y3 minus plus alpha plus alpha, that is plus 2 alpha, and here minus beta minus 2 beta. And so our task is, let me remind, to solve this system of equations for alpha and beta. And so to do so, the best way is to add and subtract these two equations one more time. So when I add the first one to the second one, then beta will disappear. So when I add the first equation to the second one, I'll get minus y1 minus y2 plus y3 plus y4, and this is equal, plus 4 alpha equal to 0. Beta disappears, plus 2 beta minus 2 beta. And so the final step is to solve this for alpha. So alpha is so alpha is actually minus, so this sum minus y1 minus y2 plus y3 plus y4 divided by minus 4. Or we can change signs and divide it by plus 4. So we can say 1 over 4 y1 plus y2 minus y3 minus y4. So this is the estimator of alpha. And now, when I subtract the second equation from the first one, what I get? I get minus y1 plus y2 minus y3 plus y4, and then alpha disappears, and 2 beta minus 2 beta, this is plus 4 beta. This is equal to 0. And I do the same. I solve this for beta, and so what I get is that beta hat is equal to 1/4 y1 minus y2 plus y3 minus y4. So that is how we can estimate parameters of this kind over based on several observations using ordinary least square method. So what we used here was OLS, ordinary least squares. And now let's find biases and mean square errors for these two estimators we have just found. So bias. Так, нет. Плохо пишет. So now let's find biases and mean square errors for these two estimators we have just found. So bias of alpha hat is the expected value of alpha hat minus alpha, expected value of the difference between the estimator and the parameter that is estimated. So, so this is the formula for the alpha hat So this is E of 1/4 times y1 plus y2 minus y3 minus y4 minus alpha. Or I can say that according to the properties of the expected value, this is 1/4 of E of y1 plus y2 minus y3 minus y4, no, not plus, minus alpha. So, and for y1, y2, y3, and y4, I will substitute their expressions via alpha, beta, and epsilon. So this is 1/4 expected value of alpha plus beta plus epsilon 1 plus y2 plus alpha minus beta plus epsilon 2 minus y3 plus alpha minus beta minus epsilon 3 minus y4 plus alpha plus beta minus epsilon 4 minus alpha. So here I have plus beta minus beta minus beta plus beta. So I have 1/4 epsilon of, here I have 4 alpha, alpha plus alpha plus alpha plus alpha, 4 alpha, and epsilon 1, so plus epsilon 1 plus epsilon 2 minus epsilon 3 minus epsilon 4. And so now I can also use the properties of the expected value. So alpha is non-random number. That is why, so this alpha was also simply put outside the expected value, as alpha is not random. So here I can say that this is just 1/4 times expected value of 4 alpha is just 4 alpha. And here I have expected value of epsilon 1 plus expected value of epsilon 2 minus expected value of epsilon 3 minus expected value of epsilon 4 minus alpha. Expected values of all epsilons are zeros, as we are told that epsilons follow normal distribution with zero mean. So these are all zeros. And what is left? 1/4 times 4 is 1. Alpha minus alpha, 0. So bias is equal to 0. That means that this estimator is an unbiased one. Now, what is for mean square error? Mean square error is squared bias plus variance. Squared bias, that is 0, plus variance. So, as for the variance, so bias is 0, And as for the variance, I will use, so I'll say that variance is variance of 1/4 times y1 plus y2 minus y3 minus y4. This non-random coefficient is squared when put out of the variance, so it is 1/16. And here, for the sum of y's, I will use the results of this simplification I have already done. So I know that y1 plus y2 minus y3 minus y4 is equal to 4 alpha plus epsilon 1 plus epsilon 2 minus epsilon 3 minus epsilon 4. So 4 alpha plus epsilon 1 plus epsilon 2 minus epsilon 3 minus epsilon 4. And then, properties of the expected value and of the variance are different. So that is why this 4 alpha simply disappears, as we know that non-random, if we add a non-random number to a random variable, this does not affect the variance. So this 4 alpha simply disappears. And then I say that variance of a sum is equal to the sum of variances for independent random variables. Epsilon are said to be independent. So that is why I say that this is 1/16 times variance of epsilon 1 plus variance of epsilon 2 plus, let me see, so minus 1 squared. So this coefficient is squared times variance of epsilon 3 plus minus 1 squared times variance of epsilon 4. And we know that variances of all epsilons are equal to sigma squared. So this is sigma squared plus sigma squared plus sigma squared plus sigma squared. So this is 4 sigma squared divided by 16. So sigma squared over 4. So this estimator is unbiased and its mean square error is sigma squared over 4. And finally, let's do the same for beta hat. So bias of beta hat is expected value of beta hat minus beta, and so is equal to expected value of 1/4 y1 minus y2 plus y3 minus y4 minus beta. Then I do the same. I say that this is 1/4 times expected value of this expression, and substitute these expressions for y's. So alpha plus beta plus epsilon 1 minus alpha plus beta minus epsilon 2, then minus alpha plus beta plus epsilon 3 plus alpha plus beta minus epsilon 4 and minus beta. And then here alphas are cancelled. So I get 1/4 expected value of 4 beta plus epsilon 1 minus epsilon 2 plus epsilon 3 minus epsilon 4 minus beta. So, and here we have the same situation. So as expected values of all epsilons are 0, so that is why what is left here, and beta is non-random, so expected value of 4 beta is equal to 4 beta, and expected values of all these epsilons are zeros. So we have 1/4 times 4 beta minus beta, that is 0. So the same situation as for alpha hat, so bias is 0, the estimator is unbiased. Then the mean square error is squared bias, so that is 0 plus variance. Then I say that this is variance of 1/4 y1 minus y2 plus y3 minus y4 then I say that this is 1/16 times variance and this y1 minus y2 plus y3 minus y4 can be reduced to this expression. So 4 beta plus epsilon 1 minus epsilon 2 plus epsilon 3 minus epsilon 4. And then I do the same. I say that 4 beta does not affect the variance as it is non-random, and so variance of a sum is equal to the sum of variances in case of independent random variables. So this is variance of epsilon 1 plus minus 1 squared variance of epsilon 2 plus variance of epsilon 3 plus minus 1 squared times variance of epsilon 4. And so the same result. All these variances are equal to sigma squared, and so 4 sigma squared over 16, that is sigma squared over 4. The same as for a hat, and actually this is an obvious result, as we see that here in our model, the model is symmetrical with respect to alpha and beta. So if we change alpha and beta, so nothing will change. So we'll get the same. The only thing will change are indices, but they are not so very important here. So as we see that alpha is unbiased and its MSE is equal to sigma squared over 4, then automatically for beta these values are the same as the situation is symmetrical. So here we solved an example on the OLS method, and we trained to find biases and MSEs one more time.